And the next one is the shrinkage method. So in the shrinkage method, the idea is to regularize or shrink the coefficients toward zero. So let's think about a simple regression problem with a couple of parameters. Let's say we have this parameter vector 1, 3, 2.0 or 3.5. Okay, this is our parameter. And in the shrinkage method, instead of having these numbers, we want small numbers, 0.1 and 0.3 and 1.2 or something. So if the coefficients are close to 0, then it's better. Okay. So if the performance is the same, then we prefer these small parameters. That's what this statement says. And how is this helpful in generalization? Because this introduces bias, which is bad, okay? But with this bias, we can decrease the variance. That's a good thing. So the total error is actually sum of bias and the variance. But while we are introducing a little more bias, but if we can decrease the variance a lot, okay? So if the later effect is more significant, then this will decrease the test error. So this is how this shrinkage method works. Okay, so basically the smaller the norm is, the simpler the model is. So we'll talk about all these things in the following slides. And shrinkage method says we have to move the values closer to 0. And when the weights converge to zeros, the model complexity decreases. To explain what this sentence says, then let me take an example here. Given a polynomial function with the parameters like this, so f of w is here, then if many w sub i's are zeros, okay, this one is a 0 and this one is a 0 and this one is a 0, so this one and this one and this one. And if many w's are zeros, then f of w becomes simpler. So let's say when n is 3, then w0 plus w1x plus w2x squared plus w3x3. Okay, then if w3 is 0, then f of w could be just quadratic equation. If w3 and w2 are both zeros, then it is just a linear model. So when lots of parameters are zeros, then we have a simpler model. Okay. So even when these parameters are not exactly zeros, but still, when the norm of this parameter vector is smaller, then the model is simpler. Okay. And actually, there's a paper saying that the model complexity is related to the norm of parameters. So here's a training error. So training error goes down. And this one is the number of random ReLU features. So we increase the model complexity here. And then the training error goes down. But when we check the norm of the parameters, it goes up and goes down. And the test error has some strong correlation with this curve. Okay, so the error is strongly related to this norm of the parameters. So there is a connection here. Okay. So now if we shrink the parameters, then that helps. That puts lots of constraint on the model complexity. Okay. So we're going to talk about how we can actually shrink the model complexity. So we will use the penalty term for the size of the weight. And objective function for unregularized regression looks like this. And to regularize this objective function, we simply put this additional term. Okay. And which means we want to minimize this error, and at the same time we want to minimize this norm of this parameter. Okay, that's what we said in the previous slide. Okay, this one, actually specifically this one is a rich regression. So we have a couple of different regularization terms here, but in this slide we are talking about some specific example of the methods. Okay, and there is a weight here, and lambda defines how much penalty we are going to put to this objective function. Okay, so let's assume that we are using a linear regression, okay, with this function. And this one is our objective functions with the regularization. And we can take a derivative with respect to w and set it to 0. Okay, then, and we can replace this y with w transpose x. Okay, and then in the matrix notation we can have this equation, and we can take a derivative, and if we rearrange, then we get this term. Okay, then for unregularized regression solution looks like this. And look at this one. So I put the color on this regularization term here and here and here. So let's compare this equation and these equations. We put this lambda identity matrix, which means when x transpose x is not invertible, then this cannot be a solution. Okay, and even when this is invertible, but still if it's almost not invertible, then this one is really unstable. So if we add the lambda I, then it means lambda 0 0. So it means we can stabilize these invert operations with this lambda term. Think about this one. When we have a not invertible matrix, but if we add this identity matrix with the scale lambda, then if we increase the lambda, then at some point this will be invertible. Okay, so regularization works in this way. And so far, we talked about only one specific example of regression method, which was rich regression. Okay, and the rich regression is based on the L2 regularizations, like this one. This one is L2 norm. Actually, LP norm is more general term, which is defined by this. Okay, so L2 regularization is rich regression, and we can put the L1 norm as penalty like this. Then we will get the lasso regression. And if we have a L0 regularization, then we can define these equations, but it's not easy to train because we have to think about the combinatorial problem here. But in this case, we can take some derivative and we can find the solution. So usually rich regression or lasso regressions are a popular regression methods. Now we can understand the regression methods based on the probabilistic model. Okay, so we're interested in posterior of W. So what is the probability of W given data samples? That's posterior, right? So we're interested in probability of W given X and T. So these are data samples, and we have a prior, and we have beta is actually coming from this. Previously, we defined the equation y is f of x plus epsilon, and epsilon is coming from Gaussian distribution with the zero mean and variance. Okay, and the beta inverse is variance. The reason why we use inverse is that if we use inverse, then the beta means the precision. Okay, the variance is talking about the scale. the width of this Gaussian, and if the variance is high, then we have a smooth curve, and if the beta is small, then we have spikes here, like this. So if beta is high, then we have this sharp Gaussian distribution. So beta means the precision. This posterior can be decomposed into these two terms, t given x and w and beta, and w given alpha. And then probability of t given x, w, beta can be defined by this one. Okay, this one. We have x and w. So we have an x and a w. Actually, sometimes we are interested in w transpose x. Okay, so w is the parameter of this function f. So when we have a w and x, then this one is deterministic. That's given. Okay, then the variance of this epsilon is given. Then the probability of t is defined by this one. So the mean is actually the function. It's basically the same thing. Okay, so the mean is f of x, and the variance is coming from this one. Okay, and then we can take the logarithm. Then we get these equations. Okay, and now second term, p of w given alpha is given by this Gaussian distribution. This one is our prior. So we can define our prior as we want. And we believe that the parameter w should be close to the origin, close to the zero vector. So mean is 0, and this one is the variance of the parameters. Okay, this is our prior, which means prior is not coming from the data samples. Prior is coming from our faith. Okay, so we can define our prior as we want. So as we said in the previous slide, we want our parameters around the zero vector. So that's why we use this prior. Okay, then when we take the logarithm, then we got this one. Okay, now we want to minimize this negative log posterior with respect to w. Then we take minus log and minus log from this one. And then we got this term and this term. Okay. And the other terms. And the other terms have nothing to do with w. There is no w here, there's no w here. So we just put constant. So it has nothing to do with parameter w. So then we can focus on this equation. And if you look at this equation carefully, then this one is ridge regression. Okay, so this one is the error, and this one is penalty term. And the alpha is lambda from the previous slide. Okay, so in the previous slide, we interpreted a ridge regression in the probabilistic model. And it means we use Gaussian prior. Okay, P of W given alpha was Gaussian in the previous slide. That's why we have this term. But we can use other distributions for the prior. So if we use Laplacian prior, okay, then if we actually calculate the posterior, and if we minimize the posterior, then it will be reduced to the lasso regression. Now we can understand ridge regression and lasso regression in the graph. Okay, so we have objective function with the contours here and here. So basically the same objective functions. Then ridge regression says we want our parameters around these zero vectors. Okay. And lots of regression says we want our parameters within these areas. So we have to minimize this loss function, and at the same time we don't want to increase this circle or this rectangle. Without the constraint, without the regularizations, then the solution should be around here and here, the same solution. But with these constraints, then we have to minimize this function, and at the same time we have to shrink this circle. Okay, so depending on this parameter, then we can find the solution around here. Then we cannot minimize this term. But if we increase this circle, then we can minimize this objective function further. So depending on this parameter, the weight, then we can find the solutions around here. So on this curve, we can find the solution. The one big difference between the ridge regression and the lasso regression is this one. In the lasso regressions, since the constraint, the regularization is making this rectangle, and this one is a curve, then it will meet this point, which means in this case, W1 is 0. W2 has some value, but W1 is 0. Think about the high-dimensional vector for the parameter W. Then this objective function will meet lots of elements of the parameter W at 0. Okay, so lots of W sub i's will be 0. So it will have a sparser model. Think about this one. Y is W0 plus W1 x1 plus W2 x squared, etc. Wn xn. Then lots of w's are zeros. Okay, then compared to this ridge regression, in the ridge regressions, w's will be small. Okay, so the value of w's are small, but still they are not exactly zeros. But in the lasso regressions, lots of w's are exactly zeros. Okay, so we talked about the ridge regression and the lasso regression, and these two approaches are really popular. Even in deep learning, we use these methods. And also there are another regularization methods like early stopping. And early stopping is completely different from shrinking method, but it's really popular. So let me introduce what it is here. Okay, it is a regularization method, and while increasing the model complexity, evaluate the validation data set and stop increasing when the error of validation does not decrease. So we can increase the model complexity. Then obviously training error will decrease for sure, and at some point maybe it could be 0. The error would be 0. But it doesn't guarantee that with the validation data set it would work. Okay, so we have to evaluate the validation data set. Okay, training data set will be used to update the parameters, but the validation data set should not be used to update the parameters. Okay, so we can use validation data set to evaluate the model, the current model, and based on that evaluation, then we can decide something about the model. Okay, it's the evaluation, not the training. So anyway, we can evaluate the validation data set, and then when the error of validation does not decrease, like this, then we have to stop increasing the model complexity. And usually in training, with the large model, then probably we can use training. iteration here. So as iteration goes, then if the model is large enough, then training error goes down and the validation error will go down, and at some point it goes up. Okay, so this one is not about the model complexity. I'm talking about the training iterations with the large model. In that case, we can use patience here. So we can probe with k times when the validation error does not decrease, because we have lots of spiky, noisy curves here. So when the current iteration is not decreasing the validation, but still we can wait for k times, which is patience. And then with k times, okay, if the validation error is not decreasing, then we can stop. And this one is the best model. So when we increase the model complexity, we can evaluate the validation data set, and then we can find the best model complexity. But in this case, when we increase the model complexity, every time we have to train the model, and then we can update. And in this case, we have a large enough the model, and then we can train the model, and at some point of these iterations, and then we can actually stop. Okay, that is early stopping. So we can understand this early stopping with the model complexity or training iterations. Another popular regularization is adding noise. The most popular one is dropout. And dropout is popular method in deep learning. And with dropout, we can turn off the half of the nodes for every training iteration. And with dropout, we can avoid co-adaptations. You can learn these things in deep learning. Okay, and the drop connect is quite similar to dropout, but instead of dropping the nodes, drop connect will turn off some of the weight. And then another one is weight noise. We can add Gaussian noise on the weight, or we can add Gaussian noise on the activations. So we can add or multiply Gaussian or Bernoulli noise to weight or node values. By this combination, we can implement lots of regularization methods. And another approach is data augmentation. So when we think about the overfitting problems, probably we have a too big model, or we have too little data samples. Okay, that is problem. So then the data augmentation could be a solution to the limited data problem, so that we can have a better generalization, avoiding the overfitting problem. So what is the data augmentation? When we have a limited data samples, then we can add more data samples. Then the question is how? Because if we just copy and paste, then we are adding the same data samples again and again and again. It doesn't help, okay, because we are not adding more information. So it's all about the amount of information. So actually we have to put more information. Then how? For example, if we are working on the image, then look at this example. This is a cat image. Okay, then if we rotate the image slightly, this is a cat too. So if we check this image and this image, pixel-wise, this one is a different image, but we know this is a cat. So slight rotation makes the same class. Okay, so that we can make a new image sample. But this is different with the same label. Okay, this rotation is fine too. Or left and right horizontal flip makes the same kind of class. Okay, in this case, and we can make it bigger, a little bigger, or we can transit the location. Then based on these operations, we can generate a lot of data samples with the same label. Okay, then we can train the network, and the network, the model will be more robust against these operations, variations. But we should be careful. As you can see here, okay, if we take a horizontal flip, if it is a digit or numbers, then the horizontal flip makes a problem. If it is a cat, then it's perfectly fine. But if it is a digit, then we shouldn't apply this horizontal flip for data augmentation. So we have to understand what kind of data we are dealing with. Okay, and then based on such an understanding, then we can apply data augmentation. Okay, what if it is a speech signal? Then how can we apply data augmentation? You have to understand a little bit about the speech signals too. Okay, so as long as we understand the data samples that we're handling, then we can apply some data augmentation. Then we can increase the number of data samples. That's how we can handle this limited data problem.